So, in the last lecture, the main idea was that there is this quantity called work, and there's this quantity called kinetic energy, and we can calculate the change in the kinetic energy acting on an object by examining the total work done on that object. We're going to change that just a little bit in this lecture right here. We're still going to look at the concept of work, and we are going to look at how it can change the energy of an object, but not just the kinetic energy. So there's a lame pun here, and it's really not that funny because it means you're going to have to deal with equations. But the equations that you have to deal with, I think, are less painful than calculating work via force times change in displacement times cosine of the angle between them. And we'll see why. Let's consider calculating the work for two different scenarios. The first scenario is you lifting a heavy object off the floor. It's on the floor, you bend down, you pick it up, you stand straight up, and you're holding it in your arms. On the floor it was motionless, and now there you are standing up, and you are motionless. So the object is still motionless, but now it's off the ground. We can certainly make the argument that you did work lifting it up, and while you were lifting it up, gravity in the opposite direction was doing negative work. But gravity is going to be one of those forces for which we have a less painful equation to deal with. Next scenario is a spring. And maybe it's just lying fixed on one end and attached to a mass at the other end. It's horizontal on a table. You grab the mass, which is motionless, and you stretch the string, and now you just hold the mass that is attached to the stretched spring. And again, you did work. While you were trying to pull the mass in one direction, you were doing, say, positive work, and the spring, trying to bring it back, trying to slow you down, was doing negative work. But again, we are going to look at a slightly different interpretation because, like with gravitational force, there is a way to calculate the work done by the spring force that is less painful than force times change in displacement times the cosine of the angle between them. We use this term potential energy for gravitational work and spring or elastic work. We can talk about gravitational potential energy, and we can talk about elastic potential energy. We use the word potential because, for instance, if you lift up this object, if you were to release that object, then you stored energy in the process of lifting it. And if you release it, this stored energy is expended as kinetic energy. And a similar thing happens with the mass at the end of a stretched spring. If you stretch the spring and you hold the mass, it's motionless. You release it, and it starts to move, and we get this emergence of kinetic energy. So we think of potential energy as stored energy, ready to be released as kinetic energy. Let's take a look at the situation for gravitational potential energy. What affects gravitational potential energy? The mass of the object. A heavier object, when you release it to fall, is going to create more kinetic energy. The height from which you release it affects it. The greater the distance, the greater the height from which you release it, the more kinetic energy it can build up. And then finally, the strength of the gravitational field. Now, you can lift it here on the surface of the Earth. You lift it the same distance on the surface of the Moon. It's not going to build up as much speed, so it's not going to build up as much kinetic energy. Gravitational potential energy is just abbreviated as GPE in many circumstances, and it will sometimes be denoted with a capital U. Potential energy in general is often denoted with a capital U, followed by a subscript to indicate the kind of potential energy in question. So obviously a capital G means that we're talking about gravitational potential energy. And gravitational potential energy is equal to mgh. We said it depended on m, we said it depended upon g, we said it depended on h. It increases with m, it increases with g, it increases with h. That agrees with what we said on the previous slide, so hopefully, at least conceptually, this formula makes sense. And it's not just conceptual, this is the formula for gravitational potential energy. I should point out, though, that a major assumption in this formula is that little g is constant. The strength of the gravitational field is constant. Close to the surface of the Earth, that's true. It would be true for close to the Moon. It would be true for the surface of Mars. It would not necessarily be true if you were, say, at the same distance from the Earth as the Moon is. There, the strength of the gravitational field has noticeably decreased from G equals 9.8, and this formula does not apply when you move that far from the surface of the Earth, or from the surface of any planet or moon. If you have that more extreme situation where you are no longer in a uniform gravitational field, you get this expression for gravitational potential energy that looks suspiciously like Newton's law of gravity. It says that the gravitational potential energy is equal to negative capital G times little m times big M divided by S. It doesn't matter what you call little m and what you call big M, but one represents the mass of the first thing, and the other represents the mass of the second thing. Capital G is still that gravitational constant of the universe, 6.67 times 10 to the negative 11 in standard units. S is still the separation between the two centers of mass. But notice that in this formula, it is just S in the denominator. In the formula for force, the denominator is S squared. And the formula for gravitational potential energy, the denominator is S. So be careful. Don't mix your formulas up. Now, the minus sign in that generalized formula, what does it mean? Because that generalized formula applies throughout the universe. As you might have noticed, you are in this universe. So that generalized formula on the previous slide applies to you right now, even though you're close to the center of the Earth. So why is there a minus sign there, but there isn't a minus sign in MGH? Conceptually, MGH, I think it is better intuitively. It's better to understand intuitively. The farther you get the object from the ground, the more effort you have to expend to get it up there, and the more kinetic energy it will have after you release it prior to hitting the ground. So there's some sense there. Gravitational potential energy increases as you move from the surface. That's true. That is true whether you're talking about MGH. It's true if you are talking about minus capital G times little m times big M divided by S. This deserves further discussion so that you better understand what I'm saying here. To understand that minus sign in the formula, start by considering the interaction between two objects that are so far apart from each other that they're not interacting at all. If there's no interaction between them, I would say that there's no attraction between them, there's no gravitational anything between them, and so I would say that the gravitational potential energy of this system is zero. So when they're infinitely far apart, the gravitational potential energy of the system is zero. There's just nothing going on between them, I hope That makes sense because that has to make sense for the next part to make sense. Let's now consider two masses that are close together. If I were to come along and take those two masses and push them apart until they were infinitely far away, because of the attraction between the masses, I have to expend energy. I have to put work into this to get them infinitely far apart. By doing work on these two, I'm adding energy to the system. I'm doing work on the system. I'm increasing the energy of the system. Well, if I'm increasing the energy of the system just to get them infinitely far apart and zero energy, they have to start at negative energy. They start at negative energy, I do enough work, I add enough energy to the system to get them to zero. So gravitational potential energy is actually inherently negative. Between any two objects that attract each other, the potential energy between them is negative. So gravitational potential energy is negative, yet we look at this formula, mgh, and it makes so much sense to us. And then we talk about positive gravitational potential energy. If H is above ground, we have positive gravitational potential energy. And we can imagine H below ground and being at negative gravitational potential energy. But we can imagine positive gravitational potential energy. How does this statement agree with my earlier universal statement that gravitational potential energy is inherently negative? These seem to contradict each other, but if I were to plot gravitational potential energy of an object as a function of the distance from the Earth, I'm going to get something that goes as 1 over s. But more specifically, because it's negative, it's going to go as negative 1 over s. And so you see these two thick black curves, they basically represent a plot of negative 1 over the separation or displacement of the object relative to the Earth. On the other hand, I don't have things get any closer to the center of the Earth than the radius of the planet. Things get a little complicated. We're not going to worry about it. We're just imagining starting from the surface of the planet. And the behavior of the gravitational potential energy as you move away from the surface of the planet, as you get very far away, your gravitational potential energy is still negative, but you're so far away that it's close to zero. The farther you get from the planet, the closer your potential energy gets to zero, but it still remains negative in this universal formulation. Where does MGH come into play? MGH resets the location of zero potential energy. For the sake of convenience, it's often nicer to measure your gravitational potential energy with respect to the surface of this large object, because on the scale of things, you're going to remain so close to the surface of the object that the gravitational field strength really doesn't change. And if we reset zero to where this thin horizontal line is, all of a sudden we see that as we move away from the planet, as we move further and further from the surface, our gravitational potential energy is increasing. We see a positive slope there. Gravitational potential energy is increasing, starting from the surface of the planet and moving away from the surface of the planet. Our gravitational potential energy is going up. So if we reset and, for the sake of convenience, just make zero gravitational potential energy at the surface of the planet, then you can say above the surface of the planet you have positive gravitational potential energy, and you dig a hole into the surface and you would be at negative gravitational potential energy. And right at the surface you would have zero gravitational potential energy. So MGH is extremely useful when you're close to the surface, but in reality It's just a resetting of where 0 is. Universally speaking, 0 is when the two objects are infinitely far apart, but we have our convenience, 0 gravitational potential energy at the surface. I hope that makes sense. So we have an expression for gravitational potential energy. I mentioned springs as another situation for which we can do something similar. We've discussed springs briefly before. Springs obey what is known as Hooke's law, F equals kx. If I stretch a spring a distance x, then there is a force trying to pull things back, and that force is equal to kx, where k is a property of the spring in question. Very stiff springs have a large value of k. Very easily stretched springs have a small value of k, and k is called the spring constant. The more you stretch a spring, the greater the force. So if I double the amount of stretch, I double the force. The force is actually changing. This is different than force in a uniform gravitational field. The force is mg in a universal gravitational field, no matter what height you are above the surface, as long as you're close to the surface where the field is uniform. But springs, the force can change quite significantly, going from just a stretch of 1 centimeter to a stretch of 2 centimeters. In fact, going from a stretch of 1 centimeter to a stretch of 2 centimeters doubles the force. The force changes very readily with springs. So how are we going to come up with an expression for potential energy? Just a little background. I'm going to skip that. Take a look at the example, but it's similar to Hooke's law. It's just a review. Let's plot force versus displacement. As x increases, the force increases. But in this graph right here, we see a constant force. This is not a plot of Hooke's law. This is a force being applied, a constant force being applied over a displacement x. And we would say that the work done is equal to force times change in displacement. But an alternative interpretation is to say that work is equal to the area underneath a plot of force versus displacement. Well, this particular force being constant as a function of displacement, the area underneath it is a rectangle. But in the case of Hooke's law, as x increases, the force increases. This plot right here is Hooke's law in graphic form. The larger x is, the larger the force is. And it's linear. S is proportional to x, and that constant of proportionality is k. It's like saying that the slope of this line is the spring constant k. This is a plot of force versus displacement when we are using Hooke's law, when Hooke's law applies. It's a triangle. We know how to find the area underneath a triangle. The area underneath the triangle is 1/2 the base times the height. The base of this triangle is the displacement x. The height of this triangle is the force, but the force equals kx. So the base is x, the height is kx, 1/2 x times kx is 1/2 kx squared. And this is the expression for the potential energy when an object obeys Hooke's law. When it obeys Hooke's law, we talk about elastic potential energy. So just as gravitational potential energy equals mgh, elastic potential energy equals 1/2 kx squared. Now there is an important difference between the two. If you use mgh, then something underneath ground level is at a negative gravitational potential energy. So you can have negative gravitational potential energy. But look at this elastic potential energy expression. K, the spring constant, is always positive, by definition. X is positive for a stretch, it's negative for a compression. You know, you can compress a spring and it still obeys Hooke's law. But once I square it, it's a positive quantity. The smallest the elastic potential energy can be is 0, and that is for a spring that is neither stretched nor compressed. That's as small as elastic potential energy gets, 0. If we take into account these expressions for gravitational potential energy and elastic potential energy, what we're effectively doing is saying we are removing them from the determination of total work, and we're sending them over to the side of change in energy. Our new expression, instead of just saying that the work is equal to the change in kinetic energy, we are separating out the gravitational force and an elastic force, if it exists. And we're saying that the total work done by the remaining forces, whether it's tension or normal or friction or whatever, the work done by remaining forces is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy. Written out in all of its gory detail, we can say that the total work of all forces except gravity and springs is equal to 1/2 mv final squared minus 1/2 mv initial squared plus mgh final minus mgh initial plus 1/2 kx final squared minus 1/2 kx initial squared. That's at least for something near the surface of the Earth. If it is something that is far from the surface of the Earth, first of all, I wouldn't have a spring, and second of all, I would have to use the more generalized form for the gravitational potential energy. But for things near the surface of the Earth, we could have kinetic energy, gravitational potential energy using mgh, and elastic potential energy using 1/2 kx squared. Bear in mind, we have revised our definition of total work to say done by all forces except gravity and springs. And if you remember, last lecture I mentioned a theorem. This is the theorem. So I hope we built up to it slowly enough and steadily enough that it's not too horrifying. When you do work on an object, you can change its speed, you can change its height, and if there's a spring involved, you can change the amount by which it's stretched. That's what the work energy theorem is kind of saying. Let's take a look at applying the ideas here. You have a toy dart gun that uses a spring, and it shoots the dart straight up. And the dart reaches a maximum height of 24 meters above where it left the gun. Now let's use the same gun, but we compress the spring only half as much. How far up does the dart go this time? So what effect is this going to have? Now you're holding this dart gun. The dart is initially motionless right before firing. And at its maximum height, once again, it is momentarily motionless. So between the beginning, at the instant it's fired, and the end point at the top of its motion, the change in kinetic energy winds up being 0. We just consider where it is initially and what its final location is, and the difference for kinetic energy is 0 in this circumstance. But how did the elastic potential energy change from the first time to the second time? And if we assume there are no other forces, then the elastic potential energy gets converted into gravitational potential energy. That's all I'm going to say. If you have questions about this, please feel free to ask at the start of class next time. Okay. I referred to The work done by all forces except gravity and elastic forces. Elastic forces and gravitational forces are lumped together under a single umbrella term called conservative forces. Other forces like tension, the normal force, the frictional force, those are lumped together under what are called non-conservative forces. In the work energy theorem, we bring the work done by conservative forces, we call it potential energy, and we put it on the right side of the equation. If we are talking about the work done by non-conservative forces, we leave that on the left side of the equation. So if you're calculating the work done by the normal force, by the frictional force, by a tension force, that appears on the left side of the equation. If you're talking about the gravitational force or a spring force, those you handle in the potential energy terms on the right side of the equation. Are there other types of forces that are considered conservative? Because it boils down to either it's a conservative force, and if it's not a conservative force, then it is just a non-conservative force. What is the distinction between a conservative force and a non-conservative force? The formal statement is that a conservative force is a force that does work on an object such that the work done is independent of the path taken. Okay, let's try and parse that statement. Let's consider gravity. We're going to take this 16-ton weight that's on the floor and we're going to set it on the table. The change in height of this 16-ton weight, it goes from a height of 0 to a height of h. So the change in height is h. Turns out that the total work done by gravity is mgh, is of magnitude mgh. It doesn't matter if I lift this 16-ton weight from the floor directly to the table, or if I start moving it around like some sort of Harlem Globetrotter thing with a basketball. It's going to finish in the same location as if I just directly brought it up from the floor. And the gravitational force only cares about where you begin and where you end. It doesn't care how you got there. So, starts on the floor, ends up on the table, that's it. That is all it cares about. The same thing is kind of true for a spring force. You can imagine a stretched object, stretched at one distance, and then you just directly move it to a different stretched location. But you could also imagine doing all sorts of motions with it from the beginning to the end. As long as you have the same beginning and the same end, the elastic force doesn't care. It just cares about where you begin and where you end. On the other hand, a non-conservative force does care about the path you take. In the little animation you're about to see, there are two identical objects, and their beginning location and their end locations are going to be relatively the same. The change in displacement from beginning to end for each will be the same. But whereas the top one is just a direct motion from left to right, the bottom one is sliding around all over the place before winding up in the same relative location on the right-hand side. The thing is, friction was acting against the motion of that object throughout its entire path. So the object that moved directly from left to right, friction only acted along this relatively short path length. So we see this short path right here, just boom, this path length difference right here, big whoop. But for the second one, throughout the entire motion, all along this twisty, loopy path, friction is acting directly against the direction of motion. And so the entire length of that twisting, looping path is taken into consideration to calculate the work done by friction. So it is a non-conservative force because it cares about the path that you follow from beginning to end. Conservative force just cares about beginning and end. Non-conservative cares about how you get there. I hope that made some sense. And that's enough for this lecture. Bye-bye.